this is Junichiro Horikawa, and this is the 9th episode for VEX for algorithmic design. And the topic today is functions. To start off, let me explain what function is. A function is a block of organized, reusable code that can be used to perform a single action or process. And this is the common concept used in programming languages, and it's the same with the VEX. Now, actually, you have already used some of the functions, which is built inside Houdini for VEX, something like add point, add vertex, attribute, and so on. So let me introduce some of the built-in functions which can be used out of the box using VEX. But before doing that, I would like to explain a little bit about a context of VEX. Now in Houdini, there's a lot of context where you can use VEX for different purposes. One major context is used for shaders, so you can use VEX to create your own shaders. Other ones could be CVEX, CHOP, and COP. Now, among those contexts, CVEX is the most general context, and which is going to be used for a geometrical modification. So the CVEX is the context that we're going to look at. And if you go to the CVEX context, you'll be able to see some built-in functions which is available for CVEX, a general purpose VEX context. In our cases, we're going to use VEX for SOP level, mostly for geometrical modifications. And there are tons of functions available for VEX, so I'm gonna show you how you can use the documentation for side effects, especially for the VEX functions, to search for the functions you want, and then read the documentation to know how you can use those functions with some examples. Now, there are several basic things you need to understand about functions. And here is some examples how you can declare your own functions. We're going to get into that later on by practicing by ourselves. But if we look at it, there are mainly two types of functions. One which can return some values using the functions, and one that doesn't return any values. Now, the main difference between two is that one which returns the values have a character or type of the values when declaring the functions, and this is the type which you will get as a result when running this process, when running these functions. And when it comes to a function without which doesn't return anything, you have this void letter when declaring the functions. And when you have this void, then when you run the functions, you don't get any result from that functions. You'll be able to run the code inside, but the function itself doesn't transform into any values. But the functions that returns value will be transformed into some values, in this case into an integer. And I'm going to show you the difference of these two functions by using one of a built-in functions from VEX. First of all, let's see what kind of functions are available in Houdini from out of the box, which is a built-in functions. By first going into the VEX page for the Houdini under sideeffects.com. Then if you go down, there's a page called VEX functions. If you go there, you'll be able to see a list of functions available. And it's pretty important to use this documentation page to see what kind of functions is available in Houdini and how you can use each of them. And if you look at the left hand side of this documentation, you see something like arrays, attributes, and intersects, and so on. So these are the categories of functions explaining what those functions are for. And on the right hand side, you have an actual functions which is available under this category. And if you click to one of the functions, you'll be able to see a detailed documentation how exactly you can use those and what this functions is for. Now I'm going to explain two types of functions, one for a void function, one for a return function, using the example from the built-in functions. I'm gonna start with the void function, and I have just clicked the function called append, and this is the documentation page for the append functions. If you look at the description page, it says as an item to an array or string. So and we have already used this actually in the array topic before. So you can use this function to add an item inside the array. Okay. Now, if you look at those gray highlighted functions, you see that there is a void characters, void letters before append. This means is that this function itself doesn't return any value itself. So this function it's not going to be transformed into any value, but it's just a void functions. It just do what it does. So it just adds a item to an array or string, and that's it. This itself doesn't become anything. Now let's see what I mean by actually using it. So make this smaller, make this page smaller, and I'm gonna bring up the Houdini window. First, I'm going to create a geometry node. Then let's create a attribute wrangle and set it to detail. And let me just save this somewhere on the desktop so that I don't lose the process. So let's try to use the function append. Okay, so when you look at the documentation page, there seems to be three types of three ways to use this functions called append. One for this one for this one, and one for this one. And each one seem to have a different kind of input parameters. Now these are actually an input parameter which you need to use or input in order to use this append, and separated by a comma character. So if you look at this one, the first void append, you see two input parameters, one which says array and one which says value. Now if you look just above these input, you see a type string just above those values, those inputs. And if I zoom this up a little bit, it says for this first type of append, it says string and string. And if you look at the description just underneath the void append, it says appends the second string to the first. So we can assume that this append works for string, and this is the base strings that which you want to input, and this what it does is that it append the second string to the first string, and you'll be able to get the updated string, updated first string. Now if you look at the second type of append, it says the type value above this first input says type, and also for the second input says type. This means that the type of a value could be anything. Same for this one. And the difference between the first append and the second append is that the second one has this square bracket, and having square bracket means is that this is actually an array instead of a single item. Now this was a single item because this doesn't have any square bracket, so it's just a single string. But for this one, this could be an array of, could be an integer, could be a string, could be a vector, and so on. and this one, this type for the second value will be the same for the array. So if the first input was an array of integers, then the second value will be also an integer. If the first one will be the array of strings, then the second value will be a single string item. So even though you have a same name called append as a function, sometimes you have several types of input that you can use for those same name functions. For this one, you have in total 3 types of append with different types of inputs. Now for the third void append, you can input the array for the first parameter, and for the second parameter, instead of using a single item, you can input an array as well. So this, as a result, you'll be able to concatenate this array with the first array. So if you have an item of 3, the size of 3, and the size of 2 for the second input, then as a result, you'll be able to update this array, the first input, into a size of 5. Now let's actually try to use this using a VEX. So I have just created a detail wrangle. I'm gonna name this as void function, and then first I'm going to create an array like int values, an empty array using array function. So this array function is also a built-in function for VEX, which creates a empty array, just a square bracket with no items inside. Okay, and I'm going to create a loop, go through from 0 to 100, and then at each iterations for the for loop, I'm going to use a function called append, and I'm going to choose the second type of append, which for the first parameter I have to input an array which I want to update, and for the second value, for the second input, I want to declare what values to store into this array. Okay, so for the first input, I want to input this values array and separate it by comma. For the second parameter, I want to input some values that I want to store into this array. So for this one, I'm just going to store the I, which is this incremented value in each loop. Okay, and as a result, after leaving the for loop, the values array will be updated. So let's check that out by storing it into a detail attribute. So accessing to a detail attribute for the integer array, you can do something like this: I square bracket at, let's name the attribute values and store the values array into that attribute. Okay, and let's check that out by going into an inspector's geometry spreadsheet to the detail, and here you are. You have just created an array, appended I value at each for loop iterations, and created as an array, stored it as an attribute. Now you might have noticed one thing when we were looking at the documentation page for append, which is this and characters before the first input array. Now when you have this and characters just before the name of the input parameter in the documentation page, this means is that the first parameter in this case is a output parameter. What I mean by output parameter is that when you run the code, something like append, after you have run the code, the first parameter, the parameter with this and characters, will be updated right after you run the code. So if you have a parameter with the and characters, that means that this is going to be the output parameter, and those output parameters will be updated when running the code. In this case, you have used the empty array for the first input, and for the first input has this and characters, which is going to be the output parameters. So that's kind of a reason at each iterations the array has been updated by adding the second values to the array, and as a result you'll be able to get this array with a lot of values from an empty array. You're using the same values right here, but right after using the append you have updated this array value. Without having this and characters, those parameters are being kept as constant values, so there's not going to be any update. So for the second values right here, like I, this value is not going to be changed, but those which has this and characters will going to be changed based on the functions, which depends on a different kind of functions, but in this case the first parameter array will be changed by adding one value to the first input array. So this is pretty important aspect of parameters when it comes to using new functions you never have used, and you need to check what kind of parameters you have to input by looking at the documentation. You need to check whether this is the output parameter or not. Now next, let's look at the return functions. I'm going back to the list of functions available, and under the arrays categories, this time I'm going to choose the function called length. Now you have also used this before. This is the functions to return the length of an array. So you can use, so these are the types of parameters you can use. Could be a vector, could be a matrix, could be an array, could be a string or dictionary. Now I'm going to use the third one to get the size of the array. So if you have 3 items inside the array, what you get as a result for this functions is 3. Now I know that this is the return function because if you look at the letter before the name of the function, it says int. Before, when we were looking at the append function, it says void, but when it comes to return function, it shows you the type of values which is returned by using these functions, and in this case it says int. So by using these functions you'll be able to transform this into a integer value. So let me show you how exactly what it means by actually using it. Okay, I'm going to copy the detail attribute, detail wrangle that I've created, and let's name this return function. Okay, and I have already created the array using append. So right after this I'm going to create a variable like named as size, and then calculate the size of the array using a length. Now comparing those two functions, append and length, you see a bit of difference. For append, which is the void functions, which doesn't return anything, cannot be stored this value, this result itself as a variable. But when it comes to return function, when you use the function itself transform into some kind of values, in this case an integer value, and that means that you can directly use this result value, which is an integer, into a variable like integer equal to size. So that's the big difference between the void function and the return function. Actually, the most of the VEX built-in functions are made as return functions, so most of the cases you can use the function itself to return some values and store it in an attribute, stored in some variable like this. And this time it was integer, but could be vector, could be string, and could be array, and so on. Now let's check the result by accessing into a detail attribute like I at size and store this size at variable into the attribute named as size. Okay, going back to the geometry spreadsheet to the detail, now I can see 100, which is the total amount of items stored in an array. Now these are the main two function types available in VEX. One is a void function and one is a return function. And try to remember what these are for. Now let's try to do some exercise using a function which have several types of parameters. So I'm going to try to use those several types of different kinds of parameters for same functions and see the different result being activated, even though the function itself is the same name. And the function that I'm going to use is called nearpoint, which says it can find the closest point in the geometry. Now if you look at the parameters type, there are mainly 4 types of parameters you can use for this function called nearpoint. And I'm going to use some of the functions, some of the options to see the difference result. Now let's look at from the first one, which is the most simple one, which only accepts 2 inputs. One is the geometry and one is a PT. And if I look at the one that's above the input, it says geometry, and above the PT it says vector. And if you go down, if you be able to see a description what those input actually is for. If you look at the geometry, you can actually check that this geometry indicates the number of input to input the points, list of points you want to look for, search for. So if you input the points to a list of points to a first input, then you want to write up you want to use an integer value 0, because that will indicate the point is coming from the first input. If you type it 1, then that means that point is coming, if you are looking at the point coming from the second input. If it's 2, then from the third input, and so on. Okay, so for the second parameter, PT, if you go down, it says the position in space to find the closest point on the geometry 2. So this is the point position you want to use for to search for the nearest point. So this is pretty simple, and as a result you'll be able to get the integer value as a return value. And there is also an explanation what this return value is by checking at the documentation somewhere around here. Okay, so as a result it returns the number of the closest point on a geometry. So by using this nearpoint, you'll be able to get the ID of the point from the first for the first parameter, and this only search against points, not the surface location of geometry, and it will return -1 if the point is not found in a search distance. So if there's no result, then you'll get -1 out of this return value. But for this first one, it actually doesn't have a distance filter, so I think you'll be able to get some kind of value if you're looking at the correct point list. Okay, so let's try to use this. Let's try to use the first parameter set to use the nearpoint and see how this works. First, I'm going to create a sphere, then create a scatter point, and create point like 100 points, then create a attribute wrangle. Let's set it to detail, and I'm going to name this as a function parameters 1. Okay, I'm going to connect the list of points into the first input of this detail wrangle, and for the second input I'm going to create a single point by using an add node. I'm going to check this one so that I be able to control the position of the point by using this. So by moving this axis, I'll be able to change the position of this single point. And what I want to do is to search for the closest or nearest point from this point to this group of points. So this will be the guide points, and what I want to do is to find the nearest point to this point from the crowd of the points. So it could be somewhere around here or here. So that's what I want to do using a function called nearpoint. I'm going to make the size of the point a little bit bigger by going into the geometry and go to the point size and raise this up a little bit so that I can see a little bit clearly. Now let's go back to the detail wrangle. And first of all, I want to retrieve the position of this point, which is inserted into the second input in order to use the first parameter set, because I have to input a position for the point to search for. Okay, so I'm going to first create a variable like named as pos and access to a second input point position, and at this point I only have single point, so I can easily retrieve that by using a point function from the second input. The name of the attribute is capital P, which is the position attribute, and then the number of the index of the point is 0, since there is only one item. So now I have just retrieved the position of the single point coming from the second input. Now that I want to use is to use this nearpoint to search for the nearest point out of this cloud of points. Now, and as a return value, you'll be able to get the number of the point, which is kind of an ID equivalent to an ID of the point. So first of all, I'm going to create a variable which can store the number for the point, and then I'm going to use a new point, and the input, the first parameter will be input number, and those crowd of the point crowd is coming from the first input, so first parameter should be 0, and then the second parameter is the position, which is this one that I have just retrieved. So writing like this. Now as a result, you'll be able to get nearest point number, so some numbers, something like 3 or 2 or something like that. If you want to check it, you can add this mpt values, create some detail attribute like named as npt, and stored it with the value you had just retrieved. And if you check by going into the detail attribute, you see a value say 2. So this point with the number 2 is the most closest point, which is closest to this point. Now let me also raise up the size of the font by going into the option, display option, and make it large. Okay, that's a better. Now if I try to move this point and something like this, and try to see the detail wrangle again for this detail wrangle, it becomes 41 now. So I guess this point is now the closest point to this point. Okay, now it's a bit hard to see from the visuals right now which one is the closest point to this point. So what I'm going to do is to, after I have found out the closest point from this point cloud, I'm going to color it to a red so that we'll be able to see it clearly which one is the closest point. Okay, so what I'm going to do is to use the function called set point attrib, which have been used to update the point attributes with specific values, and in this case I'm going to update the color attributes, which is the preserved attribute name capital C with the lowercase d, and then the number of points that I want to change is npt, which you have just searched for, and then the color that you want to apply is red, so use vector to create RGB colors. So the first value 1 will be red and other green and blue will be 0 to create a red color, and as a result the closest point will be drawn as red. And if I move this point again to somewhere else, we'll be able to see that the position of colored point will change based on the position that I'm moving, so that I can see that the near point is updating correctly. Now that was the most easiest parameter set we could use for the near point function. Now let's try to use a bit more complex parameter set like the last one. So for the last one you have in total 4 parameters, input parameters, one for the geometry, which is the same for other ones. So, and the third parameter is also the same with the first parameter set pt. So this is the position you want to use for in order to search for the nearest point. Now you have additional parameter called pt group, and at the second for the second parameter, and the max distance for the fourth parameter. Now if you look at the description for the pt group, this is kind of a filter which group to search for. And you can also use the attribute conditions like these, like if the color red is more than 0.5 and so on, or you can just directly use the point group itself for the filtering. And for the fourth parameter, max distance, this is the distance to search for the point. So distance from this point can be considered as a radius of the search. And so if this point is within the distance that I have specified, then you can search for this one. But then when the search distance is something around this size, then you won't be able to find a point. And in that case, probably you'll get -1 as a result when you couldn't find any point. So let's try to see that using this fourth complex parameter set. Okay, so I'm going to just copy this, and then mostly using the function as it is, but I'm going to change the parameter set for this one. So but before doing it, I kind of need to have some parameter set, or I mean the group filtering. So let's try to create some filter for the group by creating a additional group to those points. Okay, so I'm going to connect the group node, and let's just name the group to a half x, and set it as a point group. And I'm going to only enable the point which is with the x coordinate is more than 0. So I guess these areas, these ranges. To do that, you can do a filtering expressions for the group by saying at p.x is more than 0.0. And as a result, you'll be able to filter out, just select the points when the x-coordinate is more than 0. And I want to use this group to search only for the point which the x-coordinate is more than 0. Now I can actually directly write this for the PT group, but let me just show you this way first by using the half-x group name. Okay, so going back to the function parameters, and for the second parameter right here, this is going to be the string, the name of the group, and in this case I want to use half-x. Okay, now that was the third parameter, the second parameter, and for the fourth parameter I want to define the search distance. So let's create a parameter using chf named as dist. Then let's also promote this channel by clicking this button. You'll be able to create a search distance sliders, and as you can see now that it already shows some effects. If the value is big enough, you'll be able to, this point can find a nearest point from this point cloud. But once the slider value gets smaller and smaller, there are some time you lost a point you were looking for. The nearest point just doesn't appear anymore. And currently I am storing the result of this near point to the detail attribute. So if I look at the detail attribute, it says -1, -1. So that means this point couldn't find any closest point within a search radius. If I make it to 1, then you can still find it. But if I keep the distance between the point cloud and the base point far, then you start to lose the point. Okay, and also I have another filter, which is the group. So I am only searching for the point which the x-coordinate is bigger than 0. So if I move this base point to a -x direction, you start to lose you don't actually see the nearest point from these list of the points, but only from the points which is on the x positive coordinate. Even if you make this point close to some of the points. That is because those points are not within the half-x group. Only those points which is inside a half-x point group can be used for the near point search. Right? So by using a more complex parameter set, you'll be able to filter the point in a more complex way. And sometimes it's pretty useful. So try to remember how these parameter set works, and don't restrict yourself to use just one parameter set, but try to see the difference between those different types of parameter set and see what would be the best for your needs. Okay, and as I said, I mean, you didn't really have to create a group node like this, but you can actually use this expression directly for the PT group, and let's try to do that. I'm going to copy this expression and disable this node by clicking the yellow flag. Now there is no point group anymore, so this half-x group filter doesn't really work, but instead you can type the exact expression that I have typed inside for the group, like the x-coordinate is more than 0. Then again, this start to work again. exactly the same as using this one. So if you want to avoid using like node, group node, you can just directly enter a expression like these. And sometimes it's pretty useful because you can combine, you can create your own string parametrically or procedurally by combining like string variable all together. Something like saying plus a2s or I2a pt-num or something like that. You can procedurally create your own conditions within the VEX, so sometimes creating a group expressions within a VEX is a good idea rather than using a node, even though this seems to be a bit more simpler. Okay, so I hope it makes sense. Now let me also show you some examples how to use the function with a output parameter. Now we already have used the function with output parameter, which was append for the array, but let's try to use a bit more complex functions which have a multiple number of output parameters. Now that is what I'm going to use is the function called intersect. If you look at the description for the function called intersect, this function computes the first intersection of a ray with the geometry. So you can kind of calculate the ray of a point from a point to a specific geometry. Works just like the ray node. And you can do that programmatically. So let's try to use this. And as you can see, if you look at the parameter set for this intersect functions, you have at least 3 output parameters. Those parameter name, width, and character is the output parameters, and you have 3 output parameters. And this even also returns an integer value as a return value. So this is kind of one of the complex functions you can use, which returns the value and at the same time you have an output parameters. So if you know how to use this by looking at this document, then you're really good to go to use any kind of functions available for a VEX. So let's first look at the documentation how you can use them. So mainly there are 4 types of parameter set, and let's just limit to one type of parameter set that we're going to use. And I'm going to focus on the very first one, which have in total 6 parameters. First one is geometry, so this is the input number. The second one is the orig. If you go down, this is the ray origin point, so original point position for the ray. And the dir, this is a vector value. If you go down and look at the description, it says the ray direction and maximum distance. This function does not expect a normalized direction vector, instead it uses the length of the vector as a maximum distance to search. So it indicates the direction in which direction to cast the ray, and also the length of this vector indicates the ray distance. So more you have, farther you can reach. And the PUV is the export or output parameters, because you have AND characters before the name. And the first P is the vector, and the second U and V is the float value. Let's look at these, what these are. So NP, the output parameter P, is if the ray intersect with the primitive, this variable is overwritten with the intersection position and wall space. So this actually is the intersected point together with the ray and the searched geometry. And UV, the output parameter UV, is if the array intersects a primitive overwritten with the parametric intersection position on the primitive. So I guess it indicates the UV value of the primitive when you found the intersection between the array and the geometry. And for the return value, which is for this integer, the return value of this whole function can be seen by looking at this returns. It says the intersected primitive number, or -1 if there was an error of the array didn't intersect anything. So if it intersect with any kind of geometry, then you'll be able to get a number of primitive. If you couldn't find any intersections, then you get -1. So that will be the result for this functions. So let's try to use this. First, I am going to create a bunch of 3D points to create an intersection for. So I'm going to first create a torus, and then let's make the resolutions a bit higher. Let's also raise this up a little bit above in a y direction, then rotate this a little bit. Could be any values, but to make it a bit interesting, like this. Right, now what I'm going to do is to create a points out of this torus. I'm just going to use a scatter to create 1,000 of points on top of the surface, like this. Now what I want to do is to project this point onto a ground, XZ ground. Now currently there are no geometry on an XZ ground, so in order to create a intersections or projections, I am going to create a grid underneath its torus. And what I want to do is to calculate the intersection from each of the point, and using the cast ray going down, and if there are any intersections between the point from the point, using the directions with this primitive geometry, the ground geometry, then I want to update the point position to the intersected point positions. Then you'll be able to get a flat point, scattered point on top of a grid, like a grid, just like a projected point. Okay, so let's do that. To do that, I am going to use a intersect function right here. Now I want to activate the code for each point, so in this case I'm going to use a point wrangle. Connect the list of points to the first input, and for the geometry that I want to calculate the intersection with, I'm going to connect to the second input. And let's name this output parameter. Okay, now let's do this. First thing I would like to do is to have an empty value for those output parameters P, U, and V. Okay, so I'm going to create a vector P as a variable. I don't really need to initialize this with any values. I'm just going to create the variable like this. Same for U and V. Okay, like this. Now that I have just created an empty variable, I can start using intersect functions. Now, since this one returns some kind of values, let's first create a integer variable like inter, and then call the intersect functions. Now I want to use the first parameter set, so the first input is the input number for the geometry. In this case, the grid geometry to search for to create an intersection with. So this is going to be 1 because this is coming from the second input. Okay. And the original position for the intersect is actually each point from this point crowd. So that can be retrieved by accessing to a @capital P, which is the point position and on each point wrangle. Okay. Now you need to define the direction, which way to create a raycast. Now I just want to create the ray to a bottom direction, which is the negative y directions, so I can just create the vector like set 0, -1, 0. Now remember that the size of the direction is also important. If the size is too small, then the ray doesn't reach to there's a chance that the ray doesn't reach to the ground. So if you want all the points to reach the ground, then make sure that you have enough size for the vector direction. Okay, now after this you have 3 parameters, which is for the output parameters. So what I would do is to just input those empty variables. So P, U, and V. And after running these functions, those output parameters P, U, and V will be updated and can be used for the next code from the next line. And let's see if these values be really being updated. So it says that the P is the intersected point, and in this case it should be intersected with this ground from each of the point going down. So it should be the projected point positions. So let's see that by updating the current point position with the updated P after the intersect and see if the point has been projected. And here you are, the point has successfully been projected on the ground. Now if you move this torus to something outside the grid, or maybe I can move the grid itself to which doesn't cover the whole torus. Now you start to see some of the point didn't find intersections, and as a result the point position is not being updated. It's not going to be updated using this code. And those point, I think as a result, the result of this enter is also equal to -1. So let's check that by creating a integer attribute for each point, like saying enter, storing a intersected value, and see that attribute by going into the point attribute and look at the enter. Now if you click this, you can sort the values, and you see that there are values equal to -1, meaning some of the points has not been intersected. But if the grid covers all the torus, then you start to see no -1 value for the enter, and that means that all the point has been successfully been intersected with the ground, projected to the ground. Okay, so this is a bit of complex way to use a bit of complex functions, and since there are a lot of parameters and there are multiple number of output parameters, and at the same time you also have a return value. So this is one of the complex functions to use, but if you understand how this works, how you can read the documentation to use the function, then you are good to go with using any kind of functions available for VEX. Now I have just shown you the basic of functions, how you can use the built-in VEX functions. Now once you get used to those functions, how you can use those functions, it's time to create your own custom functions, user-defined functions. You can actually create your own code set by yourself, and I'm gonna show you how you can do that. Now, if you go to the language reference page for the VEX, for the side effects Houdini documentation page, there is a section called user-defined functions. If you go there, you be able to see a basic rule how you can create your own functions. And same for the built-in functions. Mainly you can create a returned type functions or a void functions. Now let's create starting from a void function. And if you look at some of the examples right here on this page, there is a basic syntax shown how you can create your own user-defined functions for the void. Now first you need to type void and use space, and next you type a name of the functions you want to use, and then use the parentheses, and inside the parentheses you want to type a number of parameters you want to use. For example, for this one you have single parameter for matrix called M. If you want to have multiple number of parameters, you can divide those parameters by semicolon. If the first two parameters have the same type, you can also use comma, but using semicolon is safer. So integer A, semicolon, integer B, semicolon, string C works just fine. And after this, after declaring the parameter with the parentheses, you close the code block using this curly bracket. And inside this curly bracket, you type any kind of code as a code block, and then you'll be able to create a functions. Now, just creating the function itself doesn't do anything. After you have created the functions, you actually have to call them, like calling the VEX function, built-in functions, so that it can actually run for your purposes. So let's try to follow that flow by creating your own void functions as an example. That's an exercise. Now what I want to do as an exercise to create a basic functions to create a single point position in order to use it for a spiral positions. Okay, so using a void function now. Okay, now let's try to create a attribute wrangle and set it as detail first. Okay. And let's try to create a function to determine the spiral point position by providing three types of parameters. One is the angle, one is the radius, and one is the initial position. Okay, so first of all, you type void to create a function, and then name the functions. Like in this case, I'm going to name the function as spiral pos, and create a parenthesis and close the block with curly bracket like this. Now I need to set a parameter that I want to use. Now there are three parameters that I want to set. Two parameters are set as float and one parameter set as vectors. Okay, so first parameter is the float type, which is an angle. And I'm going to separate with the comma first because the second parameter is also a float. So I'm going to call it rad as a radius. Okay, now after this I'm going to separate with the semicolon because I'm going to now use this different type of parameters, which is going to be vector. And I'm gonna name it pos. So in total I have three parameters: float, ang, float radius, and vector positions. Now if you want to use semicolon instead of comma, you can say semicolon float rad. Either way is fine. If you have a multiple continuous float values, then you can just separating them by comma as well. Either way works fine. Okay, now inside the curly bracket I actually have to type in the code block that I want to reuse by calling this spiral pass together with those 3 inputs. Now what I want to do here is to create a new point by first calculating the position for the spiral. So I'm gonna name the new positions as new pass, and first of all I'm going to use the position as the initial positions, so position plus, and I'm going to use a trigonometry to create a point on a circle by setting the angle by using angle plus the radius. So for the x coordinate I'm using cosine, and for the z coordinate I'm using sine, and then multiply all these vectors together with the radius. And inside the cosine and sine I am going to enter angle so that I'll be able to create a point on a circle of radius of a specified value right here. Okay, now after I have created the positions, I'm going to create the point using add point at this new positions. Okay, and as you can see, I mean the code itself, I have just declared the function, but I haven't really used this yet. What I have just done is just declaring the function, but in order to use this I actually need to call it like the built-in functions for the VEX. So something like use this like this with some parameters, and then finally you'll be able to use this as a function. Now let's try to use this then. What I'm going to do is to first create a initial point by, let's say, using a add node, create a single point, and I'll be able to move this around, and I'm going to use this point as an initial point position for the spiral. Okay, and so I'm going to connect this to a second input of this detail angle, and let's name the detail angle as user defined void function. Okay, and going back to the code, first thing I would like to do is to get the point position of this point connected to the second input, so which can be done by first creating a variable like named as positions, and then use point function looking at the second input by typing 1. The attribute you want to look for is the capital P, which is the attribute for the point position. Then there's only single point, so this is the index of the point you're looking for, and as a result you'll be able to get the point position of this point stored inside this vector position variable. Now I want to use this point position as the parameter for the third parameter for this spiral pass. Now in order to make it as a spiral position I need to have a bunch of points. Now but calling this spiral position one time just creates single points, so I kind of need to create multiple number of points. So let's create a for loop, like say 100, and then let's try to call this spiral position function that I have created right here. Now to do that, it's same as built-in functions. You first type the function's name and create a parenthesis, and inside the parenthesis you type the parameter you want to use. Now the first parameter is the angle, so let's derive the angle by multiplying pi, which is equal to 180 degrees. In radians it's 3.14 something, and multiply by say 0.1 to make it a small angle like 18 degrees, and then multiply this again with I, so that I have a step value at each iterations increased by 18 degrees. Okay, for the second parameter separated by comma, for the second parameter, I need to define the radius of the spiral. So I'm just going to type I multiply by 0.1. Okay, for the third parameter, I'm just going to enter the position that I have retrieved from the second input. And as a result, you have just created a spiral point just by calling the spiral position multiple times using those three parameters. And maybe by you creating, setting these values 0.1 and 0.1 as a parameter, like using CHF, like for this one for the angle, which is going to be act as a step angle value, and for this one rad and work as a step radius value. You can kind of control the outlook of the spiral. And without using these functions, you needed to copy this code inside this for loop in order to create the same functions. But by creating, organize the code that you're going to repeatedly use into a one block named as a spiral path, you can kind of have an you can effectively use the functions which you want to use repeatedly again and again. That's kind of a benefit of creating a functions. When there is a possibility you use the functions over and over again in different places, then you want to create the functions to cover wrap the functions you use. Now you have just created the simple void functions, and I think it's pretty straightforward. Now let's try to create a return functions next time. What I'm going to do is to copy all this set and convert the void function into a return function. Okay, and I'm gonna rename this to user-defined return function. Now let me go back to the documentation page and see how you can declare a return type functions. Now if you look at it, this is the basic template how you can declare the functions, and it says function, you start from function and then use space and declare the type of values you want to return, then name the function, and everything else is pretty much the same. But after this, when you want to actually return something, then you want to use a return key to actually return some values after running this code. Well, it doesn't really show it right here, so I'm gonna show it by using example myself. Now you can also declare a return function without having this function keyword like this one, but sometimes this throws you an error when VEX code confuses this with a variable itself. Sometimes it happens, so it's better you always use function whenever you want to create a returned function, return based functions. So try to remember this one, only this one. Do not try to use this one because you won't know if you get any errors or not by using this one. So always when you create a return functions, start with the function keyword and then set a type of values you want to return, then name the functions and then set some parameters, and after this write a code inside. Right, so let's try to create this as an example. Now I have just copied the void functions. What I want to do is to first replace this void with function and define the return type. In this case, I'm going to return the value as vector, meaning I want to return the value as a position itself without creating the point directly inside this functions. So I'm gonna say vector. Okay, I'm going to leave the parameter as it is. Now, after I have created the point positions using the vector, what I want to do next is to, instead of creating the point inside the function, I'm going to directly return this position that I have created by activating this code, activating these functions. And in order to return the value, the vector value in this case, what you need to do is to first say return. And then after this, you type any value that you want to return as a result. So in this case, new position, new pos. And by doing it, but when you call this functions, what you get as a result is this new positions. So this whole functions will be transformed into a vector value, and the value you get is this new positions calculated with this equations. Okay, so let's try to use this, actually use this as a function. Okay, so I'm gonna leave this line retrieving the point position from the second input, and I'm also going to leave this for loop. Now what I want to do is to, after calling these functions, what I get is the actual values as a result. And right now it doesn't show up anything because inside the functions it doesn't create the point anymore, but it only creates the point positions. Now, and this itself becomes the point positions. So you can create a variable, like a variable for the vector, and then use an equal to store the value created by a return functions and store it inside this variable. Now you can use this variable to create a point like we did inside the void functions. And the result we get is the same. So this is how you can differentiate the functions, the void functions and return functions. By using the return functions, you can actually return the resulted value as a variable like this and store it as in a variable like this to use it for different purposes. Well, in this case, it's for the same purposes, to add a point at that positions, but sometimes using returned based functions is more useful than the void functions. Now when it comes to return functions, currently I'm just using one return key right here, but actually you can create multiple return key by using together with the conditions. So let me also show you some examples using that. I'm gonna copy this whole set again, and I'm gonna leave the name as it is. Okay, now what I want to do is to update the function so that in some conditions it returns one positions, and in another conditions it returns another positions, and so on. And the conditions that I'm going to create now is based on the angle. So if the angle is in between, say, 0 to 180 degrees, then that's one conditions. And if the angle is in between the 100 degrees to 360 degrees, then return another values. Okay, so let's start by creating that conditions first. Inside a function, first I'm going to retrieve the value. Create the variable named as value, which is going to be a float. And first retrieve the angle value right here. And the angle could be a value which is in between 0 to infinite numbers. But by using a modulus equations operator together with a pi multiplied by 2, which means 360 degrees, you can change this angle value into a value in between 0 to 360 all the time, even if the value angle is larger than infinite value. I mean, close to infinite value. You can quantize the angle in between 0 to 360 degrees by using this modulus. Okay, now after this, we can create a conditions like if the value is less than pi or else. So I have just created a conditions whether the value is on the is less than 180 degrees or larger than 100 degrees. And I can do that because I made it assured that value is in between 0 to 360 degrees by doing these equations. And as a result, I should be able to get a different value, different conditions for points on the right side and the point on the left side. And those are the angle differences. Either the pi value is more than pi or value is less than pi. Okay, now let's try to create a different kind of positions for each conditions. So for the first conditions, I'm just going to copy this, paste it right here. And for the second conditions, I'm going to copy, paste it again, but modify a little bit. What I'm going to do is to first say positions minus, and then for the angle I'm going to say minus angle for the cosine and sine, and that's it. And as a result, okay, I was looking at the different angle. The left hand side and the right hand side have the position of for the left hand side and the right hand side. If we are looking the x coordinate as a vertical line, you'll be able to change the positions based on these conditions. And if you see it, you see that the result is kind of a mirrored, which is because it's based on these conditions. So the things that I wanted to show here is that you can create a multiple number of return key right like this by using together with the conditions to create a more complex functions, return functions, which is sometimes useful. Now that we have tried creating void function together with the return functions, now it's time to try out how we can create a output parameter for the functions, either for void or return functions. And let's try to see how we can do that. Now to do that, I'm first going to copy this user-defined void function that I made, and then bring it up to the right. And let's try to modify these functions that I made previously so that I can use with an external parameter, which is an output parameter. Now at this point, this is just a void function which doesn't return any values, but creating the point within the functions. Now I'm going to comment this out, and what I want to do is to output this new position that I made within this void functions using a output parameter. Now currently I don't have an output parameter, but in order to declare a output parameter, what you need to do is to first say semicolon to create another parameter, and then create a parameter starting with a keyword called export, like this, and give a space, then give any data type you want to use for the parameter you want to update, then name that parameter. In this case, I'm going to name it as spos. Now After create, now this 3 letters will create an output parameter, which is called as spos, and the data type is called equal to vector. Now what you can do now is to update this spos by using any value that you want to use as a return value. In this case, I want to use this new positions being updated for this spos. So what I can do is saying spos is equal to new pos, and by doing it, you are updating the spos with the new position that I've calculated here. Okay, so that's the only thing you need to do in order to use the export or output parameter. Now going back outside, in order to call this spiral pos functions, here's the place where you're using the spiral positions, and what you need to do is to declare another parameter, the 4th parameter. Currently I only have 3 parameters, so if I enable these functions, it will give you an error because you are missing one more parameters. And the 4th parameter is an output parameter, so you can actually input an empty variable. Say create a new variable for a vector named as spos, and just input that spos that you have just created to a 4th parameter. And as a result, this spos will be updated using this function by this output parameter, and after executing these functions, you'll be able to get a update s position and use that to create a new point. So let's try that out. Int pt is equal to add point 0 spos and see if we got the same result. And here you are. Now we have just successfully created a output parameter by using export keyword together with a data type and the name of the parameter. Easy as it is. Now I have just shown you how you can declare your own user-defined functions using VEX. Now the last thing I would like to show you is how to import a functions which is written outside Houdini, which is written on external text files, and use it in VEX. Now when it comes to import external functions, there's mainly 2 types of functions you can import. One is a built-in functions, which is available when you have installed Houdini, so which is available under a program files for the Houdini. And another one is a user-defined, user-created functions files, which you can create by yourself and be imported in VEX. The first thing I'd like to show you is how you can import the built-in functions, which is available by installing Houdini. And in order to know what kind of functions are there available when you have installed Houdini, you need to go to a folder under a program files in Windows, or a application folder in Macintosh, and then go to a folder under Houdini. Then there is a folder called a include somewhere. Let me see. Here it is. There is a folder called VEX, and under a VEX there is a folder called include. And if you look inside the include, there is a bunch of built-in functions, which is in default is not available, but by importing those files becomes available. And we're gonna try to import some of the functions right here and try to use it inside VEX. Now what I'm going to import this time is this groom.h. And if you look at the files, what it's written here is some functions which is useful in order to modify a primitive, and the first function it shows is called adjust prim length. So you can use this functions adjust prim length to adjust the total length of a primitive curve. So you can control the length of the curve by using some parameters stated for these functions. And in using default functions wouldn't be able to do that kind of things, but Houdini made it possible to do that by providing these functions as a external file. So let's try to import this functions into VEX and then try to use these functions declared in an external file called groom.h. Now before doing that, let's try to create some curve geometry so that we have some base stuff in order to control the length of the curve. Okay, so I'm going to start by creating a font and then set a rotate for the X to -90, and let's also set some values for the text. Let's just say Houdini. Okay, like this. And let's also set the size of this text. Let's say the font size be 5. And since I want to control the length of the curve, I'm going to retrieve the outline of this primitive. Currently it's just a face, but I just need the outline. So I'm going to use the primitive node, connect it with the font, then go to a face hull, choose the close hue tab to unroll with shared points so that you can just retrieve the outline like this. Now next I'm going to use the resample to increase the point number for text. Like these one have just the small amount of points, but by using resample you'll be able to have a lot of points. And I'm also going to check this resample by polygon edge. Okay, now in order to control the length of this outline, trim the outline by the length, I need to know the basic length of each primitives, meaning a parameter. Now you can calculate that using measure node, so connect that as well and change the measure type to parameter so that you can calculate the length of an outline for each primitive. Now we are ready to use the functions. We are ready to import the functions from a groom.h file and try to use the function called adjust prim length. Okay, so we're going to deal with each primitive, so I'm going to create a primitive wrangle. And let's set the name as include external function 1. Okay, and first of all, what I want to include and what I want to import is the file called groom.h, and you can import that specific file. If it's a built-in file, you can just say include double quotation groom.h close the double quotation, and this is the line that you need in order to import the file that you wanted to use, which is this one included in the include folder. And by declaring include, you'll be able to use all the functions that is inside this file, including the adjust prim length that I want to use. Okay, now let's also look at the parameter for these functions. If I say adjust prim length, you have first of all a const int geo. This is the geometry input, which input to look for. The second parameter is also an integer, which is the primitive number. And then third parameter is the const float current length. So this is the float value, which defines the current length. And the last parameter will be the target length, which is going to be the final length you want to create the primitive with. So you have 4 parameters. Now let's try to call that functions by saying at just prim length. Okay, and the primitive that you want to change is coming from the first input. So it's 0 for the first parameter, and the second parameter is the primitive number, so you can just say prim num, because you are inside the primitive wrangle. And the third parameter is the current length of the primitive, and you can retrieve that by looking at the primitive attribute called parameter, which is created by using this measure node. If you go to the primitive tab, you see this parameter attribute, so you can use this one. So say parameter. Now the last one is the actual value, the actual length you want to set the final output with for the outline. So it could be control using some parameters like length. Okay, and the maximum value of the target value should be parameter. So we could say we could use the minimum functions comparing with the parameter together with the length and choose the lesser value in between this one and this one. Now let's promote the sliders and also set some range for this value. Let's say from 0 to 25 or something. Okay, now currently the length is equal to 0, so this value is 0, the target length is 0, so I don't see anything. But if I increase this value, slowly you see that the curve is growing and trying to construct a letter Houdini by increasing this slider. So we have just successfully imported the functions from this groom.h file. So this is one of the built-in functions which is not available in default, but you can use this by actually including the file which comes with a Houdini installation. And this function is pretty useful in some cases, so you can remember how you can use this, how you can import this file. Now you can check what kind of functions is available as an external file by going into the include folder, looking at the installation folder of Houdini. If you go look one by one, you'll be able to see what kind of functions are there. And there are some useful functions out there. So try to look at each of the files and see if any functions is useful for your needs. Now unfortunately those functions are not documented properly in the side effects documentation page, so you gotta find it by yourself. Now these are the file which is coming together with the Houdini installation, but this time next thing I would like to do is to create your own external file so that you can import the file that you have created by yourself. So let's try to do that. And let's try to give this function, user defined return function 1, this function be saved externally and try to import this functions from a external file. Okay, so what I'm going to do is to first copy this file, copy this code, then open up a text editor, any text editor, and then paste the code and save this, and save the file in the same directory where you have saved your Houdini file, and inside a same directory, which in this case I have saved my file on the desktop. So inside the desktop I am going to create a folder called include, and inside include I'm going to save the file as something.h. So in this case I'm going to say something like spiral.h. Okay. So I have just created the text file called spiral.h, and which is inside the include folder, and the include folder is in the same directory as this Houdini file, right? So keep that in mind, and let's try to import that file and use the function that I have declared inside a spiral.h. Now, first of all, I'm going to create a attribute wrangle, and then set it to detail. And first of all, first thing I would like to do is to import the file that I have just created, and you can use the same include keyword like this. Now you cannot just say spiral.h, because this only works when you are using the built-in functions, the functions coming with the Houdini installation. Any other files which you have created by yourself, you have to specify the path for that file. So to do that, first of all, you need a double quotation like this, and the current hip file directly can be written like a $ plus capital hip, and in this directory there should be a folder called include, and inside include I have saved the file called spiral.h. So this is the path that you want to look for, and this is the path where you have saved the spiral.h file. Now let's also name this include external function 2. Okay, now I am also going to create a add node, connect it to a second input, create a single point, going to be the base point for the spiral. Now is the time to use the functions from this external file. So first of all, I'm going to retrieve the point position from the second input. So vector pos is equal to point from the second input, position at first point. And I'm also going to create a loop for 100 times, and inside the loop I'm going to retrieve the point position for the spiral. I'm gonna name the variable as npos, and here's the place where I want to use the function called spiralpos, which is stored inside the spiral.h file. So I should be able to just call spiralpos and say pi multiply by chf ang multiply by I, then I multiply by chf dot radius, then position for the third parameter, and promote those angle and radius. And finally, after retrieving the position value using spiralpos function, I'm going to create a new point using addPoint functions and see if I get the same result. And here you are. You have just successfully imported your custom functions from the external file called spiral.h and use it for your own purpose. In this case, creating a spiral positions, and this worked just fine. Now I have just shown you how you can use the functions from an external file, how you can import those functions from an external file. And whenever you want to use the same functions over in different number of wrangle node, then using saving the functions in external file is a good idea, because without importing a external file, in order to use the same functions, you have to copy and paste the same functions over and over again in every node you want to use it. So if you know that you're using exactly the same functions for each node, then it is a good idea to save the functions into an external file and import it like this. Now I have just shown you the basics of functions, what you can do with it, and with some examples how you can use it. I hope you get the glimpse of it, because at least using the built-in function is pretty important. How to read the documentation is pretty essential. And if you get used to it, creating your own function is also useful, and saving it as an external file is also very useful when it comes to use the same function over and over again in different places. And this is it for function, and for next topic I would like to talk about volumes. What is the volume, how you can control volumes with VEX, with some examples. And this is it for today, and thank you for watching. If you like the video, please subscribe and try to watch the next topic as well. Thank you very much, and goodbye.